We're going to talk a little bit about friction today. The next few days are going to be rough because it's like every day we're going to be talking about something new because we are a little bit behind. I would love to slot in some extra days, but it's going to be tough. Luckily, at least for today, our conversation shouldn't take too long, provided that you guys kind of understand what we're doing and what. So let's start with some of the questions that are on the board. What's friction? When does it happen? What contributes to increasing or decreasing your friction? Who could help me out here? So what's friction? Awesome. So let's start with just, getting some characteristics down because, understanding why it happens goes beyond the scope of this course. But if you could understand kind of like how to categorize it. So the first thing that Imelda said is it's an opposing force. It's good. So friction acts to oppose motion. So we always know its direction. That's important. So if I'm going this way, I go 180 degrees opposite the direction I'm going, and friction is going that way. If I go on an angle like this, friction goes 180 degrees from that and goes against me. It's always acting to oppose motion. Now, why does it happen? Or do we have anything else to contribute to the categories? So it's an opposing force. Does it happen when you are still, when you're rolling, when you're sliding, when does it happen? Anytime there's movement. Good. So it doesn't matter if you're stationary, if you're rolling, if you're sliding, if you're doing a combination of rolling and sliding. If there's movement, there's friction. What do you need in order for friction to happen?
Two objects.
Excellent. Two surfaces. Because one might not be an object, right? Because you can have, you can have friction between an object, a solid object, and a fluid, or a solid object and a liquid, right? It doesn't have to be, it has to be two surfaces. So when two surfaces are touching each other, automatically we have friction. Good. All right, so we're looking now, we'll move past that idea, and because I think we nailed down the two things that are the most important. Number one is that it acts to oppose motion, and number two, that we need two surfaces involved that are kind of moving across each other. Now, the biggest of the frictions actually isn't one when you're moving at all. The biggest of the frictions is actually the friction that holds things in place. We call that static friction. Now, in the honors class, we only learn about static friction. In the AP class, in the college level class, we learn that friction doesn't only exist to hold things in place, it keeps on working while you're moving, doesn't it? You guys kind of know this. If you're driving in your car and you're going 40 miles per hour, and then you just put the car in neutral and turn the car off, what's going to happen as you're moving? You're going to slow down and slow down and slow down, and friction will eventually take you to what? Zero. So you'll end up with a net force that's in the opposing direction, right? You'll end up with an opposing force being your force, and you'll end up stopping. So friction works when you're moving, and it works to hold you in place. Luckily for us, the math is going to be the same. What changes is just one of the variables. So let's talk a little bit about that last question, which brings about what are the variables. So what variables happen to contribute to your friction? How do you think friction might be affected by things that happen in nature?
If you're going faster, you have more friction.
So if surfaces are moving over each other faster, there's more friction. That's an awesome theory. Is it true? No, it's weird though, because you would think if a motor is running and you make the pistons run really, really fast, that the amount of friction is increased. The amount of friction is the same. The longer you run the motor, the more likely you'll be to have a problem. The amount of heat might be different, but the heat's being generated from more than just friction. That's probably where there's a little bit of confusion.
Is the type of surface affect friction?
What do you mean?
Like, is there less friction on ice than there would be on, like, sandpaper?
That's awesome. Well, what do we call that? So the comment was made, if I'm walking on ice, let's say I keep the same shoes on, right? Because otherwise we're having too many variables, we're going to get confused. So let's say I'm walking with my rubber-soled shoes on ice. Won't the friction be less than if I'm walking with my rubber shoes on the sandpaper strips that we put on stairs to prevent slipping? What's the answer there? Absolutely. So what do we call that variable? Let's just call that the texture of the surfaces. The texture of the surfaces definitely matters. So if I'm rubbing sandpaper on wood, I'm going to get a different level of friction than if I'm running metal across wood, right? The frictions will be different. Even if I apply the same forces and do everything, same speeds, the whole deal, I try to change nothing else, friction's definitely going to be different. What's another thing that would contribute? There's only two, so if I get lucky and you guys hit the only two variables that are in the equation, one after the other, that'd be great. Well, the angle contributes to the second one, yes. Oh, thank you. That's a big hint. The angle contributes to the second one. Remember when we were talking about running up the hill and down the hill? Is it easier or harder to keep your footing than if you were running on a flat surface? Harder. Why? Why is it harder to run up a hill than you feel like you might slip a little bit more? Okay. And what changes as you get closer to a 90-degree angle? Well, no, that's not the amount of gravity, but the amount of your gravity that does what? The amount of pressure you're putting on the two surfaces. So if it's you going up a hill, right, we talk about the support force causing the hill being your normal force. The normal force, or that support force, is the pressure between your shoes and the ground. If the angle keeps increasing of the hill that you're climbing, the amount of your normal force goes down, and the pressure between your shoes and the surface go down, and the friction, therefore, will go down. Now, let's use an example where we're not using our own weight to create that pressure. Let's say that you are sanding a project in your woods class. If I press down harder between the sanding block and the surface that I'm sanding, don't I create more friction? Sure. Right? The pressure between the surfaces definitely matters. In fact, those are the only two things that matter, is how rough the surfaces are and how hard we press them together. Those are the two big things. So how do we write that? Well, looks like this. The force due to friction is equal to mu, the Greek letter for m, which I will explain here in a second, times the normal force. Now, mu describes the texture of the surfaces. We call it index in physics. It's the first of many indices that we're going to learn this year. An index is just, well, you guys tell me, what's an index? Forget about physics for a second. Just tell me what the word index means. Where do you find one? Back of a book sometimes, right? And what does it do for you? It references pages. It's a reference. So when we talk about indices in science, we're usually talking about some way to compare different values of measuring the same stuff, right? So when we say that is an index that tells us about the texture of the surfaces, it means that if we look at mu values, the bigger mu gets, the bigger friction's going to get. the rougher the surfaces must be. The smaller mu gets, the smoother, the slicker the surfaces must be, right? So maybe steel on ice, the mu is going to be really small. Sandpaper on sandpaper, the mu value will be really, really big. But going back to what Carolyn told us, mu's always going to be between two surfaces, isn't it? There's no such thing as, oh, well, I'm going to check what the mu is on my gym shoes. It's always going to be your gym shoes on what, right? Because my gym shoes, the mu between my gym shoes and this floor is going to be a lot different than the mu between my gym shoes and the ice on a skating rink. That's why if I try to run full blast on a skating rink, I'm going to wipe out with the same exact shoes that would give me perfect traction on cement. Because the mu value changes. Therefore, the friction changes. Okay? So this just tells us the texture of the surface. It's an index. We're going to be able to figure it out in the lab for a bunch of things. We're going to do that. And then this tells us the pressure between the two surfaces. That's it. That's all that it takes to figure out friction. Now, look up here. Equation for two types of friction. What changes? Well, the only thing that changes is mu value will change when you're moving compared to when you're not. It actually goes down. So the static friction mu for my gym shoes on this floor will be higher than the kinetic friction once I get going. So as I'm running across this floor, the coefficient of friction for shoes and the ground, the same ground, will be less than if I were just standing here and somebody were trying to push me. It's weird, but luckily for us, at least, we're not learning a bunch of equations. All we're doing is saying, okay, if it's moving or not moving, the only thing that's going to change is mu. The normal force isn't going to change, but mu will change, and my friction will actually go down if I'm moving. So kinetic friction is going to be, in most cases, slightly less than static. Okay? Figuring it out always like this. So let's practice. We've got a box. And the box is being pulled across the floor by a 20 Newton force. The force produces an acceleration of 2 seconds. Calculate the force of kinetic friction for the system. So we're obviously assuming that we're moving the box across the floor. First question I have for you. We're going to do this problem together. So the first thing I would want you to do is what? What do you think? I would want you to do a free body diagram. Good. And if you're asked for it or not, I don't care. That's where you should probably start. So if you do a free body diagram, it kind of helps you to map out what forces are happening and where so that you can see what the unbalanced force might look like. So what do you have here that we can map? So my 4 kilogram box. What? Let's see. Ingrid, give me one force. Oh, the normal force. Okay. You're starting with a hard one. All right. Fabian, give me another one. What's the one that's obvious every time?
Wait.
Yeah, wait. I know you meant pause, but it's the same word, isn't it? Yeah, so we've got our weight going down like that, right? What else we got going on here? We've got some lateral forces happening, don't we? So what do we have? What's the 20? That's force applied, or accelerating force. And what else do we have going on here? Well, I'm looking for the coefficient of friction. What else do I have happening? Friction. Which way is it going to point? Opposite the way I'm going to move. So I've got force due to friction like this. Now, I think everybody realizes that there was no intention whatsoever from the author of this problem to have the box crash through the floor. So what are we going to assume about the normal force that Ingrid gave us and the weight that Fabian gave us? They're going to be equal. So the up and down part of this problem just goes away. They cancel each other out. Now, this part of the problem is what we want to focus on. Now, we know the value of this force is 20. Right? So where do we start our problem? Where do we start all of our Newton's laws problems? Here, right? And this is what? What is this always, if we want to make a substitution? What does Newton's second law say? F equals ma. So I'm going to write just m times a equals force accelerating minus the forces that are opposing. Now, I'm going to make two more substitutions. Pay attention. So we've got m, which I know, and a, which I know, minus the opposing force, which in this case is friction. I'm going to make these substitutions one at a time. So everyone is follow along. I know some of you are 5 steps ahead of me. Over here, we're going to write 4 times, what's the acceleration? Equals 20 minus the normal force. Actually, I said I was going to make them one at a time. I made 2 this time. Because I substituted in M and A, and then I substituted in what the equation is for the force due to friction. So here we determined that the opposing force was friction. Here we put our only equation for friction in. That's the only way we could figure out friction is the equation. So now, the only thing we got to do is figure out, well, what do we know here? Well, the first thing that I do is say, okay, I know what force due to friction is. Does everyone see that? It's going to be 8 minus 20, or how much is that? Negative 12. So negative 12 equals negative mu times the normal force. So what's going to happen to the negatives? All right. And this, I know. Does everyone see that? Because 12 equals mu times the normal force, which is 40 newtons. Remember when we learned how to figure out normal force and we said that it was weight cosine angle? Well, the weight is 40, the angle is 0, and the cosine of 0 is what? And what's 1 times anything? Itself. So then we have 40. So now, what's the thing I don't know? The coefficient of kinetic friction. Oh, by the way, that is the fancy physics term for the texture of the two surfaces, right?